This is a video from Math 120, section 2.2. So we're talking about limits here, and we're going to investigate them kind of like we did with the charts in section 2.1, but we're not going to be filling in the charts for some of these. We're going to fill in one line at a time. So let me grab my calculator here. So I want the limit as x goes to 0 sine of 3 pi over x. So I'm going to, in y equals, I'm going to put this sine of 3 pi over x. Now you could go to math and use your fraction button n over d. You may not have that fraction button, so you would want to put parentheses 3 pi over x. So 3, the pi is here above the caret, second pi over x. And the xt theta n key will give you the x you need. Now that I have that in there, I can compute various answers for this particular function. So I want f of 1. So if I use alpha calc, that'll give me this little pop-up menu. The alpha calc takes me to f4. It's like a function key on your keyboard, but it's a function key on your calculator here. So I want y1 because I just put that into y1. I need function notation, f of 1. Enter, and it's going to tell me that's 0. So my first answer is 0. So I'm going to do the same thing, so I'll go grab this, but I want f of 1 divided by 4. So that's a little closer to 0. I want to know what's going on as x goes to 0. This is read the limit as x approaches 0 of the sine of 3 pi over x. So I can see this says 4e to the negative 13. That's almost 0 because negative 13 means 1 over 1 with 13 zeros. So that's a really small number. So that's 0. So what if I put 1 over 6? So I'll go grab this again. Put 1 over 6 in. And I got something that's small again. It's not quite as small as this one, but it's still incredibly small. The negative exponent there tells me that's 1 with 4 and 11 zeros after it. 1 over that. And it's negative, so it's oscillating a little bit. And sine does oscillate. So what we're doing is picking a sequence here that looks like it's going to 0. So everything looks fine, but that's not really what's going on here. This is heavy oscillation, and a limit fails to exist when you have heavy oscillation on a function like this. So even though this is nicely defined, except for where x is equal to 0, we could find the limit if we actually have just a hole in the graph, but this is heavy oscillation, so the limit will not exist. They ask you to continue all the way down the page here, finding the function values here. I'm guessing that a lot of these are going to be 0, but you want to go and figure out each one. Now some of you have a TI-83, so to go back up to this, you'd have to do a second enter, and then take you up to the next line. And some of the early versions of TI-84, that's also true for. Also, if you wanted to get the y equals, so I'll go ahead and do the 1/8 while I'm here. If you wanted to get the y equals, I'd have to do a vars, y bars, and function y1. So instead of using the alpha trace, I could also get the y1 from vars. I can't just type y1 because it's not the same thing. y1 in the calculator is a specific symbol. So when we finish this, it's going to actually show that our limit here was 0 because the numbers that we were looking at, if we just had a chart and we didn't know what the graph looked like, would actually be going to 0 because we picked just the right numbers for it to approach 0 as x goes to 0, for x approaching 0 to end up being 0, the y value is 0. But our graph shows us that that's not true, and there's a little explanation given here. We're going to try to find the limit again, which means as x goes to 0, this is going from the left and the right side. So as x goes to 0, this is for plus or minus 1. This happens to be a symmetric function, a y-symmetric function. So the negative 1 value at x is going to be the same as the positive 1 value of x. And in this case, it's 0.84147098. So this is a very nice function, sine x over x, except for when x equals 0, and it's not defined there. But the reason it's not defined is that there's a hole in the graph. So there's a more interesting thing that's going on here. So we end up with a hole in the graph. This is one of the typical functions they use to describe some things that are strange when we're working with limits. So if we construct the table, there it is. There's also a video example here, so you can look through that. We're going to see the table looks like this, and getting closer and closer to 0, because it says as x goes to 0, the limit as x goes to 0, and this is the notation, LIM, x goes to 0 underneath. The limit as x goes to 0 here should be, it looks like 1, so it looks like it goes through 1. You can put this in your calculator and you'll get the same graph as what you're seeing here. So for the next function, in number 3, they're giving you a piecewise function here and asking you to find the limits from the left and the right. And I would say the limit from below 2 on the other side of 2 to the left of 2, and the limit to the right of 2. So if I'm looking at 2 here and I ignore the right side of it, just look at the left side of it, that would be the 2 minus. It looks like if I traveled on this graph and I got there that I'd be at 2. So the answer for this would be 2. But if I go to the right side of 2, if I get on the graph and travel there, then it looks like I'd be going to 0. So these have completely different limits from the left and the right. Now if those limits aren't the same from the left and the right, the whole limit can't exist. So D and E is what we will write. Does not exist. So number 4 is asking you about particular limits. We don't have a graph to look at, but they tell me that the left limit is 2 and the right limit is 4. So there's definitely a gap in the graph, and we call it a jump. So you'll answer these questions. Approaches is the wording that they use, and I say goes to. They're both acceptable and have been around for both a long time. So either way works. So the limit as x goes to 3 from the left is what this says, or the limit as x approaches 3 from the left. To summarize, looking at a graph, there are 3 problems we could see for limits. A jump we already looked at. There was a gap between 2 values. We looked at that, I think, in problem number 2. Heavy oscillation we looked at, and vertical asymptotes can be a problem. So if I had a graph that looked like this, you want to make a sketch of this so that you can work along with me. If I have a graph that just looks like this, you're going to see that there's heavy oscillation right here at 5, 2, 3, 4, 5. So there aren't any problems before 1. At 1 there's a jump. All the way to 2 there are no problems. I can get on this graph and travel there. No problems for the limits. At 2 there's a vertical asymptote. So on one side the limit's going to negative infinity and the other side is going to positive infinity. And then there's heavy oscillation at 5. So to summarize this, I have at 1 there's a jump. At 2 there's a vertical asymptote, VA. You can write vertical asymptote if you want to. And at 5 there is heavy, and I'll let you get away with writing OSC. Heavy O isn't enough. OSC is what I need. If you're going to spell it out, spell it correctly, please. So I could also ask you these kinds of questions. What's the limit as x goes to -1, that should be -1 there, from the left of f of x? So this would be the graph of f of x, the whole thing here. So it's piecewise and it's got some crazy things going on. I could also ask you the limit as x goes to -1 from the right of f of x, the limit as x goes to 2 from the left, the limit as x goes to 2 from the right, and I usually don't write limit real clearly, but it's LIM of f of x and f of x. And the limit as x goes to 5 from the left, and the limit as x goes to 5 from the right of f of x. So these are the kinds of problems you would see me ask you on this type of problem. So I'll give you a graph, and then you'll have to answer me, what are the limits there? What are the problems? Where do they occur? So I have 3 problems here. I have a jump, I have a vertical asymptote, and I have heavy oscillation. So from the left, it looks like the graph is going to -1. So I ignore the other side. I'm only interested in the left, so the rest of the graph doesn't matter. It doesn't matter if this is a closed circle or an open circle. Holes are not a problem for limits. So it's basically, if I travel there and I get there, maybe whatever I thought I was going to no longer exists there, but I could certainly get there on that part of the graph. We do the same thing from the right. So traveling on the graph from the right, from the positive side, from above the x, above -1, is going to get me to 2, it looks like. Looking here, one of the answers for this would be does not exist, because it's not actually defined. The limit isn't defined. But a better answer, if you're going off to infinity, is to state which kind of infinity you're looking at. So from the left over here, I get on the graph and I travel, and I'm going to keep going down. So this means it's going to be -infinity. And on the right side, I get on the graph and travel towards 2. So that's this way, traveling towards 2. This keeps going up and up and up, so that would be +infinity. Those would be the best answers for the vertical asymptote. And then at 5, I have heavy oscillation to the left, so this does not exist, because at heavy oscillations, the limit is not going to exist. And then from the right, there's no graph there, so that limit doesn't exist either, because I can't travel on anything to get there. So 2 does not exist for 2 separate reasons. There was nothing there on the last one. Now, if I look at the whole limits, the limit as x goes to -1 from the whole limit of f of x, so x goes to -1, period. I want to compare these two. If these are the same, then the whole limit would be whatever these numbers are, but they're not in this case, so the whole limit does not exist. DNE stands for does not exist. So either limits exist and you can give them a number, or they don't exist and you'll write either a -infinity, infinity, or a DNE. So this one, the limit as x goes to the whole limit of f of x. These two would have to be the same. They're not the same, so this one does not exist. If they were both positive infinity or both -infinity, then I could write whichever infinity I had, but they're not both the same, so it doesn't exist. The whole limit here, of course, doesn't exist because neither side of it existed anyway. So the next few are very similar to the ones that I just did on paper. So holes are not problems for limit. When you travel from the left side of 5, in this case, x is 5, travel from the left side of 5, the limit is what the y value would be if I could get there. And from the left and the right, it's going to the same place, so even the whole limit exists here. Pay attention to the left and right. Down here it's 1 minus. This means go to 1. I'm at 1. And I want to go on the negative part. That's the one to the negative x-axis. If it said 1 plus, I would be on the other part. So the limit from 1 minus would be 4, and the limit 1 plus would be 7. So the limit as x approaches 1 from the left is 4, because that's what the y value would be if we could get there. The holes don't matter. Limits are fine with holes. So here they also ask you for the function value, so that's what the y value is. The limit value is determined by getting on the graph and traveling there. So the whole limit at 5, no problem. We can go from the left and from the right. The whole limit is 8. So the limit as I approach it is going to actually go to 8. But the function value is not defined. there's a hole in the graph here. There is no x value all along x equals 5. There is no y value, rather, along x equals 5. The next exercise only has one problem on the graph. You can see here there's actually a jump here. It's not defined either at 4 or at 2, but it is defined here at for y equals 3. So for the x equals 3, there's definitely a problem on the graph. It's a jump. At 0, there is no problem. If there's no problem, then the limit will be the function value, because approaching 0 means to approach from the left and from the right, and they both go to the same place. No problems. Like the road down on 74. Getting into Wingate, you come on the road from Charlotte, and coming from Wadesboro, you're coming on the road or Wilmington, you're coming on the road from the east, and you end up in the same place. You end up in Wingate. So you think of these as kind of like roads. No problems anywhere. Right here, there's definitely a problem. These two roads don't come together. We've got a problem. They also ask you for function values here, so be very clear. F of 3 and the limit as x goes to 3. These four have four completely different solutions. So just be careful as you're answering that. Number 7 is very similar to what you will see on the test, and it has pretty much everything except for a vertical asymptote. So I might even throw a vertical asymptote in. There's a hole here. There's no problems for the limits, but it does not have a function value defined. There's a jump. There's another hole. There's some heavy oscillation going on. Then there's a nice rainbow over here. It looks like a parabola. I say rainbow. So just answer these carefully. For number 8, they're asking you to look at the graph. So let's actually look at the graph here. We can also look at the table. So y equals, I'm going to put in 3 over 3 divided by parentheses 1 plus e is above the ln. So second ln, and I'm going to put in 1 divided by x. So we're interested in 0, so I might go to my window and actually put in an x-min of -1 and 1, so that I can look at it. We'll graph that. So it looks like I definitely have a jump at 0. It's going somewhere at 0 from the left and somewhere at 0 from the right. Now, one way to examine limits here, you could get on the graph and trace it. You can see from the left, it looks like it's going to 0. When I got to 0, see the x equals 0, there was no y value, so I know it's not defined. This y1 here is not defined at x equals 0. But I could instead change my table and take a look at my table of values. So here I want to start the table at 0, but I want things really close to 0. So I'm going to put in a delta table. Instead of 1 here, I'm going to put in 0.00001 and see if we can get some interesting numbers here. So if I do second table, notice that the x values are small, and I'm getting errors on the y values. Now if I'm getting all errors on the y values, that tells me that I've probably put in something that's a little bit too small to get these correct. But from the left, I can clearly say it's going to 3, and I'm pretty sure it's going to 0 from the right. So the graph is going to 0 from the right. If I scroll a little bit further, this is giving me errors everywhere. So I'll go back and set that up, second table set, and instead of 6 zeros, maybe I'll put only 5. 1, 2, 3, 4. Now I want to set that back to 0 because I'll have to scroll too much if I don't. So second table, and I'm still getting error. Let me go back and set my second table set. I'll put this at maybe 0.001. So if you're getting nothing but errors, you put something in that the calculator can't handle, so you want to make sure that you change that. So this is second table, and now I'm getting some numbers a little bit closer in here. See the 0.005? But notice that we got negative exponents. So I'll do one more second table set of 0.01. Second table. And I can see that these actually do go to 0. That's really small. Negative 43. This is 1 over 1 with 43 zeros. That's a really small number. If I scroll up, I can see that still with 0.01 as my delta table, that's 3. Now this is exploring what happens as x goes to 0 from the left and right. So I've made it very close to 0, this 0.01. So like we did on the tables in 2.1 and earlier on a couple of examples in this section. So now I know what the limits are. I know that the whole limit doesn't exist because there was definitely a jump there. On the next problem, number 9, they're asking you to sketch an example of a function that satisfies all the conditions. So starting from scratch, this is a little more difficult, but this isn't asking us to start from scratch. It's giving us some examples. So as x goes to 0 from the left, we want to go to -1. That graph does. This graph does not. It's real easy to see it. 0 from the left, so it's approaching 0 from the left. I'm going to get on the left side and travel, and it needs to go to -1. That one is. And then as x goes to 0 from the right, it goes to 2. That one is. And then it wants the function value to be equal to 1. There's a closed circle there at 1. So it looks like this is the graph. For number 10, the x values aren't equally spaced, so it's not probably going to be easy to get these x values by going through the calculator like this. I would start with y equals and put in the function, clear, parentheses, x squared minus 7x, close parentheses, divided by parentheses, x squared minus x minus 2. They're asking for 6 decimal places here. This will be on the test. You might have as many as these numbers to put on to your problem. So you should be able to do this pretty easily with your calculator. So I'm going to go in here. They are not asking for the secant, the slope of the secant here. They're just asking for the function values. So this isn't too difficult at all. I'm going to go into stat, make sure my function's right, and it is. Go into stat, edit. I want to clear out all these lists. Remember that it's clear that you want. And I could have cleared these by doing clear all the list. There's another way to do it, but this is just as quick, so no problem. And I'm just going to type these numbers in. So my observation here is that as it's going to, it looks like -1. These first numbers here would be approaching -1 from the right. It's from above -1. These numbers are smaller than larger than -1. And then from -2 to -1.001, those would be approaching -1 from the left. So you want to think about the numbers a little differently now. This is a calculus concept of limits. So I want to get the function value, so I'll go to the tippy top of list 2, and I'm just going to put y1 in there. All of you can do the bars, y bars, function y1, and then I need parentheses. I'm going to put second list 1 in here. You could do these one at a time if you want to, but it seems like such a waste of time to do them one at a time. So if we're putting 0 in, we get 0. In order to get the 6 decimals that they're asking for, and of course if it's only 1 decimal you only put 1, you'll have to scroll down. So you can see immediately at -0.9 we end up with a whole bunch of decimals. So we have -24 point, we'll need 517, 2, 4, and 1 we have to make the decision. The last one we have to make the decision. If the 7th decimal is 5 or bigger, we're going to round up. Otherwise, we just get rid of the stuff back behind. And this one isn't, so we just get rid of the stuff. So we'll write -24.517241. If you're having issues with rounding, please talk with me at my office hours, and we can get that cleared up. It might be that you were taught incorrect rounding in high school. Now this is going to ask me to guess the value of the limit as x approaches -1. And that's from both sides. So if it does not exist, we're going to enter none. But on my test, you're going to enter DNE. So WebAssign and what is typically done in calculus are two different things. But WebAssign, make sure you're paying attention to what they say. So if I look at this, it looks like my answer is -2665, right? That looks pretty good. But if I look at the other one approaching from the left, I get 2668.8. They're not even the same signs. So it looks like I've got a vertical asymptote there. I can corroborate that by going back to my window. Well, actually, let's do y equals is where we put this, right? We have that equation in. I'm going to do a zoom 6 because I know I played with the window last time. And around -1, right in here, I've got a vertical asymptote. It goes off to negative infinity on the left, and it goes off to, backwards. It goes off to positive infinity on the left, and on the right, it goes to negative infinity. Just a little hint here, if they ask you to make your own table of values, it's really not necessary. You really could look at the graph like I'm looking at the graph here, and use the table with the delta table really small. This is around 0. So I'm going to show you what I would do on these problems. They just want an answer. I'm not asking for the table. I will ask you a problem like this and expect that you do it in your calculator like I'm about to do it. So in y equals, I'm going to put the square root. I need parentheses, second square root of x plus 4. I'm going to get out of that square root, so I have to go over 1 because -2 is not under the radical. Put parentheses, and I'm going to divide by, I only have one thing in the denominator, but some of you are not going to be conscious of, if I'd had 2x there, that you'd have to put parentheses in for 2x. So you might want to go ahead and put parentheses around your numerator and denominator, either one. Of course, you could use the math button, the fraction button, for making this into a fraction. Now, I'm interested in what's happening around 0. So I'm thinking second table set. I want to know what's going on at 0. Down here, I would have put in 1 and put in something really small for the delta table. So I'm going to try a 0.001 here and see if I get a good response. So I know at 0 I've got a problem because there's a 0 in the denominator. I'm expecting to see an error there. But right here I've got 0.25. If that's to the right of 0. So the limit to the right of 0 is definitely 0.25. To the left of 0, I can see it's also 0.25. So I can easily get my answers here. I'll do the same thing down here, but it will be to 1. So the difference in problem number 12 is that instead of 0 from my table set, I'll set that to be 1. I would need y equals to be x to the 4th minus 1 divided by x to the 10th minus 1. Now both of these factor. If you've done some higher level factoring, then you know how, we know for sure 1 comes out of here, and you can do synthetic division to see what the remainder would be if you divide it by x minus 1. So if I look at my table, you can see my table starts at 1. I've got 0.3988 there, and to the right I have 0.4012. Now because they're close, it seems like what I need to do is make my delta table a little smaller. So I'll make my delta table maybe 0.000001. The e's will make it upset pretty quickly. You end up with errors everywhere. But oftentimes, and I forgot to set my table set to be 1, so let's do that. So second table, I get 0.4 to the right and 0.4 to the left. It's hard to tell left and right, but notice that the numbers before 1 would have been up above, and the numbers after 1 are down below. So when I'm looking on my table, going down the list is to the right, going up the list is to the left. Another thing you might consider doing is actually looking at the graph. So if I do a zoom, well, I already did a zoom 6, so let me do a graph. And it shows me a graph. I have no idea where that goes to. I could do a trace, but I'm not really interested in what's going on around x equals 0. I'm interested in x equals 1. So if I trace over to 1, so somewhere in here, see the 0.4? And then after it looks like 0.25, so it would be very difficult to see what that is. We could zoom in again. Zoom in 2 at 1 would be good. See if that helps us any. So if we trace over, first I need to trace, and then I hit the left and right. So at x equals 1, looks like 0.4 and 0.37. If we zoom in as again, zoom in as 2, hit trace again, I'm looking at x equals 1, 1 and 0.9. So I could kind of get to see that the limit was 0.4 there. And this is just function values. This isn't secant, this isn't slopes, this is just function values. In 2.1 we were talking about slopes, in secant lines and tangent lines. These are just function values. So it looks like the easiest way for me to get good answers for this is to actually look at my table. And that's what we had here on the table. So the answer would have been 0.4. Number 13 has you fill in a chart again. This is just function values. You're going to put this in to y equals, put all these numbers into your stat menu, and then figure out what the y values are. So in the tippy top of list 2, you're putting in the y equals y1. y1 of list 1. So we did one like that. Estimating the limit, again, you can do just on your graph. Well, not on your graph. You could do it on your graph, but the easiest place is to do it using your table. So if they don't give you a table of values, I wouldn't expect you to make up a table of values, and that's what they're kind of saying here. But we can do a little better than that on the calculator using our table and using a delta table of something really small. The last one's going to ask you true or false, so be careful, think about it carefully.